Okay, here's an example of graphing with calculus. Now, it's gonna feel like cheating a little bit because I'm doing this on the computer, and I could produce a halfway decent graph of this function with a few clicks. But as I explained in class, even if you have a computer or calculator, you can be very misled into thinking you understand things, or even have a decent graph when you don't, if you don't really have a way of analyzing things by hand. So we're going to try and do this by hand as much as possible, and then I'll let the computer do it at the end. So here's a function, and in class I'm going to go over the first part pretty quickly because we did some observations in class. It has some symmetry, and that is that f of minus x is equal to f of x if you check, and that's an even function. And so that's going to be y-axis symmetry. That halves our workload because we really only have to look at the right-hand half of the graph. So that's cool. It has, if I look at the infinities, or I sometimes call them, I don't know, I have various names for this, but I guess infinities is pretty good. In other words, what happens on the far left, far right, far top and bottom of the graph. So in some things that come as part of that are going to be, are there vertical asymptotes? And of course the answer here is no. And in fact, while we're at it, we might as well note that it's a polynomial, so it's continuous and differentiable everywhere. That's really nice. There's no dropouts. The domain is all of R, all of the real line. There's no asymptotes. There's no cusps or corners. That's wonderful information to have. And what about horizontal asymptotes? Or other end behavior. In other words, what happens if I take the limit as x goes to infinity of f of x? Well, that's going to be, I put this polynomial in there. And what we know about polynomials and rational functions is that we can just look at the leading order term. And that is going to go to infinity. And in fact, I can be very efficient. And this is not too surprising. We can put a plus or minus here. And you get the same behavior. And we know that's because of the symmetry, the evenness of the function. And that's going to be infinity. Okay, so on the left and right hand sides, it's blowing up, as polynomials tend to do. Okay. Intercepts are interesting, and the signs are interesting. If we know where it crosses the axis, then we should also think about where is it above the x-axis, where is it below the x-axis. First of all, let's get the y-intercept right out of the way. That's just going to be f of 0. We should always calculate that, and that's going to be 12. That's easy. And then x-intercepts, I don't want that in math mode. X-intercepts, that's going to be where f of x equals 0, or in other words, x to the 4th minus 8x squared plus 12, equals 0. Now, this is a great example for a lot of these things. It's a great example of the fact that this is a toolbox, not a method, not a step-by-step method. If this turns out to genuinely be too hard to solve, then just drop it. You might want to just not try to find it. In this case, I made sure that this would actually factor. It turns out, as someone observed in class, it's x squared minus 2 times x squared minus 6. And so x squared is either to 2 or 6. And so x equals plus or minus root 2 or plus or minus root 6. Okay. The plus or minus is, again, coming from the evenness of the function that you're going to get the symmetry in the x-intercepts. Okay, so those are nice to know. And then what else is there to know? Well, what other interesting points might there be on a function to plot? The idea, one of the ideas here, is that we don't want to just start plotting a lot of random points and connecting the dots. We're going to get a very crappy graph that way. But if we could identify and plot all the interesting points on the graph, then that'll be good. And the most interesting points after the intercepts, and sometimes even more interesting than the intercepts really, are going to be like the maxima and minima and the inflection points. Or in other words, and you might as well do all the critical points because you're going to find them anyway. So critical points, which can be rest, uphill rest, downhill rest, or maxima and minima, they all come from f prime of x equals 0. Now f prime of x is going to be 4x cubed minus 16x equals 0, and x factors out of that. In fact, 4x factors out of that. And then you get an x squared minus 4. And so that's going to be x equals 0 or plus or minus 2. Aha, so there's going to be 3 critical points. Now, we would like to get a sign chart for this thing. And that's going to be useful. Why don't we go ahead and get the second derivative so that we can do it all at once. And that's going to tell us about concavity and inflection points, which are the places where the concavity changes. F double prime of x is going to be 12x squared minus 16. If I look at the zeros of that, let's see, a 4 factors out again, and so 0 equals 3x squared minus 4. X squared is 4/3. X equals plus or minus, surprise, surprise, 2 over, fraction, 2 over root 3. You can rationalize that if you want, but it's not too important. Okay, so that's where the interesting points are. And then the question is, do we need a full sign chart for this thing? We can actually get away without it. It'd be a good idea to make a full sign chart for the first derivative and this for the second derivative. But sometimes we can get away without it. Let's actually just plot these points. Let's make a table. Let's say f of x. Okay, so what are some interesting points? Well, when x is 0, f of x was 12. I'll put that in math mode, doesn't matter. And then when x was equal to, what was the next one we found? Plus or minus root 2 or plus or minus root 6. Those are good to know. Alrighty, so plus or minus root 2 both gave us 0. And plus or minus, oh, sorry, that was a little confusing. When I've got it zoomed in like this, it hops around a lot. Those were also x, y equals 0 points. And then plus or minus 2, we found those to be points where the derivative was 0. Let's actually plot those guys. Let's actually make a table. We're actually going to have to plug them into f of x. Let me put that in up here while I'm at it. F of 0 we already knew was 12. F of plus or minus 2, we actually plug that back into our original function. We get 16 minus 8 times 4, which is 32, plus 12, which is equal to minus 4. Okay. So those are good points to plot. And then the last pair were the inflection points, or what looks like inflection points. At least they're zeros of the second derivative. What do we get when we plug into there? Well, that I think I'm going to want to write out. F of that. Oh, let's make that look a little prettier. There we go. Okay, so it's that to the 4th minus 8 times that squared plus 12. Let's just make sure we're putting the right formula here. Yep. Okay. And okay, so that's going to be 16 over 9, because root 3 squared is 3, and then squared again is going to be 9, minus 8 times 4/3 plus 12. Okay, so it's going to be a little bit of a complicated number. We're going to put it over a common denominator of 9. 16 minus, and then 32 times 3 is 96. And then 12 times 9 is 108. And 16 minus 96 is minus 80, so we're going to get 28 over 9, which is approximately 3, because 27 over 9 would be 3. Okay, so let's put in the 28 over 9 here. Okay, that's probably all the data we'll need for that table. So there's some interesting points to plot, and we know why we're plotting all of them. These are x-intercepts, this is the y-intercept, these guys are critical points, these guys are probable inflection points, although we really should be, before we say that, we should make sure that the cavity really is changing. Okay, so if we just plot all of those points on the graph, so what I'm going to do is I'm going to cheat using the calculator here. I'm going to go back up and grab the function. Let's come back down. And plot that thing. And let's imagine that instead of the calculator doing all the work for us, that we have actually plotted those points, and then we want to think about connecting the dots. I would be doing that by hand, but all my by hand methods are being annoying to me with the technology right now. So let's look at a view where we only go, the biggest x value that we were interested in was 2, so let's go just to like minus 2.5 to 2.5. And the y's, we've seen that there's a minus 4 that's of interest, so let's say minus 5 to like 10. Try that out. And I'll indicate on the graph where are the points that we would plot by hand, and how would, oh, you know what, I forgot the 12. That was very silly. 15. Okay. Oh, actually, I forgot. Root 6 was an interesting x value. So let me take the x out further. Okay. So here's how this would work by hand. You'd plot the 0 to 12. You'd plot the 2 and minus 2, comma minus 4. You know those are critical points. And you'd also know, we also know that eventually it goes up, 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 and up, 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 up on the far left and the far right. And there's no critical points past 2, so it pretty much has to just start up and then keep going up and not do anything interesting. Similarly over here. So without even doing a sign chart, which we could have done, we can figure out that these two are minima, and this one's a maximum. It's not that hard to figure out. If this one's the big one and these two are small and there's nothing else going on, it's got to have this W shape. But if we had been paranoid about that, we could have carefully done a sign chart that would have said minus, plus, minus, plus. And that's a good way to really dot your I's and cross your T's if you want. Then the other points that we were going to plot are the intercepts. Root 2 is there, and root 6 is there, it turns out. We know root 2 is around 1.4, and root 6 is about, I guess, yeah, 2.45, something like that. And so those points we can plot. And then the other points were the inflection points. 2 over root 3, if you calculate on the calculator, it's a little bit more than 1. And then the y value is just a little bit more than 3. And so there it is, right about here. And here, we would have plotted these points. So I'll just highlight the 1, 2, 3, 4, 5, 6, 7, 8, 9 points. And in fact, of course, remember, we only really had to do this right half if we wanted to, and then just flip the graph to get the rest of it because of the symmetry. And plotting those points, just the max, inflection, intercept, min, intercept, and then zoom off to infinity, we get a very good qualitative graph of what this function is. Even if we didn't do a terribly good job of sketching the graph and connecting the dots in between, nobody's going to be able to accuse us of having a misleading graph, even if it's not super pretty as perhaps the computer can do for us or the calculator can do for us. So that's one example of using calculus techniques to get a graph of a function.